Okay, so today we're going to start looking at how to solve Unit 4. Unit 4 begins today. Unit 4 is about solving quadratic equations. So this is going to be, a lot of this is review, but some of it's not. The stuff today will pretty much all be review, I think. But I think it's important review. So we're going to start off by looking at factoring stuff. We'll review factoring today. There's a bunch of different methods we're going to end up using to solve quadratic equations. And our goal is, I want to talk about this just for a second before we start the unit. Our goal is, for you guys, is to be able to pick the best technique and use that, the best method, right? What are the ways, just, we're not going to go into a lot of detail, but can you tell me some ways to solve a quadratic equation? So I could use the quadratic formula, right? And we're gonna use that, we'll get to that one fairly soon. Quadratic formula, give me on a scale of 1 to 10, how hard or easy is that?
It's really easy.
I mean, it's long, isn't it? There's a lot of simplifying, probably like a 6 or a 7, kind of something like that maybe, right? 10 being really hard, 1 being really easy, right? So that one's sort of middle of the road, maybe slightly more difficult than some other methods, but sometimes it's the only way to do it. In many cases, it's the best or only way to do it, right? What are some other ways? We can't really use substitution to solve an equation. But you remember solving by factoring? Where you factor and then you apply the zero product property. Is it ringing a bell a little bit? Maybe we're going to review it all, so don't panic if it's not. But that's a really easy way to do it, if it works. If the factoring is easy to do, that's a really simple way to solve a quadratic equation. And so that's like if it's easy to do, it's like a 1 out of 10. It's super simple to do, but you can only use it when you can use it. You get my point here? Yeah. There's a bunch of, and there's about 4 different methods that we're gonna talk about, and some of it will be review, some will be new. 4 different methods for solving quadratic equations, and your job is going to be, okay, I want to look at the problem I'm trying to do and decide what's the best way to do this. First of all, what's the best way to do it, and then do that, get the answers, right? So that's where we're going. Today we're going to look at maybe just begin to talk about, review one of those methods, which is solving by factoring. Now we're not actually, today I don't think we're going to have enough time today, and I don't want to try to jam too much into one day. We're not going to have enough time today to get to a point where we're solving a lot of equations, but the most important ingredient for solving by factoring is factoring, right? So that's what we're going to review is factoring. So add a couple things to your notes here. Solutions to a quadratic equation are the points at which the function intersects the what? You fill in the blanks. If I were to graph a parabola, graph a quadratic function, the solutions are where the graph intersects what? The x-axis. So the solutions, we could also refer to these as, what's one way to talk about it is solutions. We could talk about them as zeros, roots, or x-intercepts. Now we'll come back and revisit this idea here a little bit later, because it turns out that sometimes solutions to quadratic equations don't show up as x-intercepts, right? And that won't make sense right now. I can't give you a good reason why that happens without talking about complex numbers, and we haven't gotten there yet, right? But for real numbers, these are all pretty much interchangeable, okay? But when we get into some non-real numbers, then we got to be a little more careful how we use our terminology, okay? So what about the number of solutions? And I want to amend this just a little bit. When I say number of solutions, I mean real solutions, real number solutions. What would the graph look like if there were 2 solutions? Yeah, it's going to intersect the x-axis in 2 places. So there's one of the infinite possible examples where I end up with 2 x-intercepts. Okay. What if there were only 1 solution? Okay, so what's the point that would be on the x-axis there? Well, but what if, maybe, but in general, what do we call that point? The vertex, okay. So here's another example of one. And we'd say in math that it's tangentially intersecting. the x-axis. It's only intersecting it at that one point, right? It's a tangent. The x-axis is like a tangent to that curve. But if that language isn't super familiar to you, that's all right. It's not a big deal. We'll talk a lot more about that in calculus. What if there are no real solutions? Doesn't touch, okay? So this is going to be the case where the solutions that we're going to get are going to be non-real. So to start things off, I threw in a couple problems. And on your assignment here, by the way, or on your handout, this is really a kind of a silly way to do it. It says find the solutions to each quadratic equation by graphing. Okay, well, we would never graph first and then manually by hand and then go look for solutions. In an advanced class, that's a horrible way to approach it. You'd never do that. You'd find the solutions algebraically, or if you have technology, then you could use a graph and quickly get the solutions with the technology. So here's an example. So what if we want to do a problem like that one? So we want to find all the zeros of that function. Okay, so how are we going to do that using technology? Graphing calculator, or even better, Desmos. This is only, we're going to spend like a minute on it, showing you how to do it with a graphing calculator, and then the rest of the time it's all about solving it algebraically. Yeah. Okay, so all we would do then, if we wanted to solve this graphically, which is the way you're going to do it in college. I mean, that's the way in a science class or in the real world. If you're an engineer, you'll just solve graphically. You're not going to do a lot of algebra. We'll just define the function. Okay, and what am I looking for? Yeah, right there, right? And notice in Desmos, those will already show up as little gray dots, right? When I click on the function, it already suggests those are some important points. It suggests that's an important point. These are the ones I would want, right? So then what are my solutions? And positive 2.449. Now, what's the obvious disadvantage here of solving this graphically? Is it giving us exact answers?
Yes.
It's not. It's giving us decimal approximations, right? It's not giving us exact answers, which is the downside. So you got to take the good with the bad, I suppose. I'll just add this to our notes here. So if that's the graph, then what would I input into Moodle? Well, I would just input negative 2.449, positive 2.449. Now, it wants them rounded to the nearest tenth, so I actually wouldn't do that. What would I do?
Just 2.4.
Negative 2.4, right? Everybody see why that's 4? Oops. Okay, makes sense? And then what if the parabola never crossed the x-axis? Well, then there would be no real solutions. Right? Questions on that? And we've already done stuff like that, but I just wanted to remind you that how we can use technology to solve these quadratic equations. Okay, now let's focus on how we can do this using factoring. So we just want to review some factoring. So let's start off. I'm just going to take some examples off of the handout I gave you. Let's look at, like, how about start off with problems 1 through 4. We're just going to practice finding the greatest common factor, do a couple quick examples. Let's do number 3. Okay, so we're going to find the greatest common factor, or the GCF. So talk to me about the greatest common factor. If you had to explain that to somebody in a class that's a lower level class, how would you define the greatest common factor? Say it again. Okay, so for numbers, it would be the biggest number that divides evenly into all of the numbers, right? So what's the greatest common factor of 14 and 35 and 14 and negative 35 and negative 7? 7, okay. All right, so we're going to get a 7 for the number part. But what about the variable part? It's okay, it's going to be, the answer is m squared, but why? Okay, because that's the biggest thing that's going to divide evenly into all of those terms, right? Okay, now let's think about why that is. If I've got an m to the 6th in this first, let's just break each of these terms up, and we're going to represent them pictorially here. So the first one, I've got an m times 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 an m, right? Next one, I've got an m times an m times an m. And the next one, I've got an m times an m. Well, how many m's could I divide into each of those products? Only 2, right? I can't divide, if I try to divide each of these by m times m times m, that's not going to work because I don't have an m to cancel with that on the top. Everybody agree? So in each case, I could do this, right? I could divide each of these through by m times m. And I know you guys know these rules, but I just want to just show you visually how this works. That works here because each of those are going to cancel, and I just get a 1. The top and the bottom cancel, right? Here, 2 of the m's, the factors on the top cancel, leaving me with 1 left over. And here, 2 of the factors on the top cancel, leaving me with 4 left over. Right? Everybody see that? But the most I can undistribute or factor out would be an m squared. Okay? And why is that? This is the greatest common factor of this expression because 7m squared is the biggest thing that divides evenly into each term. Right? Okay, so if I wanted to factor this then, what would I get? So that's my greatest common factor. Let's see what actually would be left over. So 14 m to the 6th minus 35 m cubed minus 7m squared is equal to 7m squared times what? Okay, how'd you get that? Yeah, right. Okay, think what it means to factor out a greatest common factor. If I'm factoring out a greatest common factor, I'm just dividing it away. Let's look at a really simple example with just numbers for a second first. Then we'll come back to one with variables. All right, so what if I had something like 9 minus 12 plus 15. Now, I can simplify those by just adding all those up, but let's not do that. Instead, let's just factor out the greatest common factor. What is the greatest common factor of each of those numbers? 3. It'd be 3, wouldn't it? So this whole thing is going to equal 3 times what? What's going to be left from that first term? 3. Second term? Minus 4, right? And then the last term? Okay, how do I know that's true? Because if I distribute the 3, it takes me back to my original expression, right? You would. Yeah, because if this is an equation, and let's prove it. 9 minus 12 is negative 3 plus 12 is 12, or plus 15 is 12, right? How about over here? 3 minus 4 is negative 1, plus 5 is 4, times 3 is 12. So we need that 3 there, don't we, to get an equal number on the left and the right side of the equation. Agreed? Okay. And so when I say the sentence, factoring out a greatest common factor is the same thing as dividing something away from each term, you see what we mean. It's just undistributing, isn't it? Factoring out a GCF is exactly the same thing as reversing distribution. We're just factoring out what we would redistribute to go back to where we started, right? If I were to distribute the 3, I just get that, right? So factoring and distributing are just opposite processes. If I take this whole thing up here, this whole expression, and we apply some arrows to this, to go from here over to here, we call that factoring, because we're breaking it into a product of factors, right? What do we call this if we go from here back to there? Distributing, we call it distributing, we call it multiplying, we could call it expanding. They all are just synonyms for the same thing. Usually the math word we like to use is expanding. Okay, but they're just opposite processes. So now let's take our more complicated example. So what are we going to get here? Well, if we're factoring out a 7m squared, that means that we're dividing it away from each term, right? So then 14m to the 6 divided by 7m squared gives me what? 14 over 7 is 2. M to the 6 divided by m squared is m to the 4th. So there's the first term when we undistribute. What about the next term? We're going to get minus, let's do this one. So 35m cubed divided by 7m squared. Negative 35 over 7 is negative 5. M cubed divided by m is, okay, and then finally, over here, 7m squared divided by 7m squared is what? Is negative 1. Okay, so there, that's factored. Right? We get that? We broke up these 3 big terms into a product of one greatest common factor and some smaller terms. Okay? Questions? Okay. All right, so let's try another one. How about number 4? Okay, so we want the greatest common factor. So what is the greatest common factor? Now look at each of those terms. They've each got a number, right? And they've each got an A and they've each got a B, right? So we gotta take it in three parts. What's the greatest common factor of 3, 5, and 8? 1. So we can't take any numbers out, right? We can't undistribute any numbers. What about A? What's the biggest power of A that I could divide away from all three of those? A to the 1, right? Because that's the, and how do we know? The greatest common factor is going to be the least common power, right, of a base. So the base A is being taken to the 1, it's being taken to the 2, and it's being taken to the 1. So the greatest common factor of all those powers of A is going to be the least common power, right? Smallest common power, which is A to the 1. So we're going to get A to the 1. I don't really need to write the 1, do I? And then what about the B's? B. Okay, and then what's left over? What's the other factor that's left over when we divide A times B away from each term? Okay, I'm going to get it. Everybody agree that's going to be a 3B?
Yeah.
Okay. Minus 5A, good, plus 8, good. Okay, and so on the assignment, we're just asking for the greatest common factor, and that would have been A times B. Okay? All right, so moving on. How about some review, and I'm sure you probably haven't done this in a while, but this will come back in a hurry. What if we wanted to factor some simple quadratic trinomials? So trinomial, tri just means 3, right? So we're going to factor some quadratics that have 3 terms. So here's an example. We'll do number 5. So what's that going to equal if we write this in factored form? Think back to Algebra 1. What's the game we play here? Okay, so each of these factors, I'm hearing people are moving in the right direction. So each of those factors is going to be, how many terms? 2, okay? What's the first term of each factor going to be? X, okay. Go ahead, Gabe. Question, comment? Okay, good. And so the game we're playing here, now these are simple quadratic trinomials, and the reason I'm calling these simple ones is because A is equal to 1, right? Everybody see that? The coefficient of x squared is 1. So these are they're either going to work or they're not, and they're really simple. We know that when I break this apart, those have to be x's, and here's the way you can kind of prove that to yourself. And I know you get that. I mean, everybody remembered that part. But when all is said and done, I ought to be able to go between those two forms, right? I've got the ax squared plus bx plus c form, and then this is what we're going to call factored form, right? I can break that apart into a product of factors. Going from here to here, we call factoring. Going from the bottom row to the top row, that's expanding or multiplying. So if I were to FOIL these out, wouldn't everybody agree that when I FOIL these out, when I distribute the x, I'm going to get an x squared? Yes. The question is, what are the numbers? What are the numbers that are going to make this thing work? So what do they have to do? What do the numbers have to do here to give us this trinomial? What's the game we play? Have to find 2, 3, have to, okay, they got to multiply to 45 and add to 14, right? So when we're looking for magic numbers, here we always want to find the numbers that multiply to c and add to b, if we're dealing with simple quadratic trinomials, right? Now, you can play a sign game here, and you don't really almost need to very much when you're dealing with simple ones, but when we get into more complex quadratic trinomials, the harder ones where a is not equal to 1, those are a little trickier. And so we want to make sure we can get the signs correct before we even find the numbers. They have to multiply to a positive and add to a positive, correct? So what are the signs guaranteed to be of the two numbers? They have to be positive, don't they? Right, so we can already put plus signs there, and that makes it a little bit easier. And then what numbers do the job? 9 and 5. we got it. Okay, we'll try another one real quick. Just to warm up. Okay, so what are my variables this time? What are the signs going to be? Okay, both negative. How come? Okay, they multiply to a positive. If two numbers multiply to a positive, what does that fact tell you? The two numbers are what? Same sign. Either both positive or both negative. But if they're the same sign and they add to a negative, they're both negative. You're already thinking about this the right way. And so what numbers would those be then? Multiply to 26 and add it. Okay, good. 2 and 13. Okay. Piece of cake, you're getting this. Okay. Okay. Oops. Okay, what about this one? So I've got an n squared, so I know I've got n's, right? And then what numbers multiply to 1 and add to negative 2? Negative 1 and negative 1. Good, because I know the numbers both have to be negative, right? Okay, everybody get that? They multiply to a positive and add to a negative, and then what numbers multiply to 1 and add to 2? That would be a 1 and a 1, so it's negative 1 and negative 1, right? Okay, how would I write that, though? That's not the most simplified way to write that. Yeah, I would write that as n minus 1 squared. That's a perfect square. That's a perfect square, isn't it? So this was a perfect square trinomial. How could we have seen that? Well, for it to be a perfect square trinomial, what would the constant have to be that we combine with n squared minus 2n? Well, it'd have to be half of b squared, right? Remember that stuff? So half of b would be negative 1, squared is 1. So it fits the pattern for a perfect square trinomial, doesn't it? Right? Okay. Do you have to, sometimes algebra books, they really harp on recognize, I don't think you have to be so vigilant about memorizing a formula that tells you whether it's a perfect square trinomial. You just find the magic numbers, and if you get the same magic number twice, then it's a perfect square, isn't it? Okay. Let's keep going. Okay, so what about this one? That looks like a harder one, doesn't it? Because a is equal to 2. So are we stuck? What do you mean? You see it. What? Yeah.
Well, since we get 4 and 10, we have times 2, so I guess it'd be like actually 4.
Or okay, yeah, you're thinking too hard here. Okay, good. So this is a really important point, and I think it actually shows up on your notes. I think on your notes it says something like on page, what is this, page 3, it says when factoring, always look for a what first? Greatest common factor. We're always gonna try to factor out the greatest common factor every time we factor stuff. We always wanna try to do that first. So we always ask ourselves, is there a greatest common factor? Yes, there is here. What is it? 2, right? 2. The biggest thing that will divide evenly into each term is just a 2. So I could rewrite this as 2 times what's left over. Okay, good. So we got a GCF. Always factor out the GCF first, if possible. Right, so in this case, it was 2. All right, now can we go any further? Yeah. So if I want to write, if I'm trying to write this in factored form, that 2 is stuck there. And that's a real common mistake that people make is they forget the 2. Okay, what are the other numbers we're going to get? Magic numbers. We get K's. What do you think? Now this time, what are the signs going to be? Negative and positive, because they multiply to a negative. So the pattern, I try to be as consistent as I can. The pattern I always follow then is I ask myself, okay, if they're going to multiply to a negative and add to a negative, which is the bigger of the 2 numbers, the positive or the negative? It's got to be the negative, because when I add them up, I had some leftover negative, didn't I? So let's put the biggest one first. And now what are the numbers? There you go, negative 10 and positive 2, and that's my answer, right? How do I know that that's my answer? Because I can't break it apart anymore. There's no more factoring that I can do. So if I want to write something in fully factored form, it means I'm going to break it apart into the smallest possible individual factors, right? Like, for example, if we were to, this takes us back to when we were doing factoring trees with numbers. Like if I gave you something like, oh, what if we did 72, and we want to break that up into its prime factors, smallest possible factors. What would you do with a factoring tree? Okay, we could do 9 and 8. What's the 9 going to break up into? And whenever I get to a prime, did you guys circle them?
Yeah.
Okay, so the 8's going to break up into, okay, I got a 2 and a 4, and the 4 breaks up into a 2 and a 2. Right? So then if I wrote this thing in prime factored form, it's going to be 2 cubed times 3 squared, isn't it? You see that? So I've got 2 times 2 times 3 times, 2 times 2 times 2 times 3 times 3. If I break it up, but I can't break it any further because each of those numbers is prime. Same thing when we're factoring an algebraic expression. We want to break it up as far as we can, right? Okay, so now let's look at, well, I got one more. Before we go any further, one more. Factor this one.
This one not on there.
No, not on there. No, what's the problem?
I didn't.
Okay, there are no magic numbers that work, are there? So in factored form, if I want to write this in factored form, that's it. Can't go any further. There are no convenient factors to get out of that one, right? Okay. How much time we got? 4 minutes? Okay, so here's where we leave for the day then. Now let's try some harder ones. So now we're going to try some where A is greater than 1. So something like this, like what if we had, okay, so I know today was pretty elementary, but I wanted to kind of start quick, start easy with factoring, right? So what about something like this? Is there a greatest common factor this time? There is not, so we're stuck with the 2 there, right? So now, what are we going to do? What are we going to do? We have to kind of shift into second gear here. We got to do another approach to this. I just want to know, we can't finish this today, but remember back to Algebra 1. Did you guys learn bottoms up? Oh my gosh.
What?
Okay, how did you guys do this? How did you get?
What?
I don't remember, but I know this.
I
Okay.
have never heard of this in my life.
Okay, so you found magic numbers, you multiplied 2 times 18, and we'll go through all this tomorrow. But we would do 2 times 18, you always multiply A times C, which would give us 2 times 18 equals 36, and then what? Then you gotta find magic numbers that do what? That multiply to AC and add to B. So what numbers would multiply to 36 and add to negative 15? Negative 12 and negative 3, right? So my magic numbers this time, my magic numbers are, what did we say, negative 12 and negative 3? Okay, now here's, I'll go through this once really quick, and this, you may not remember all this, but we'll rehearse these steps tomorrow. If I use bottoms up, tell me if this is how you did it. So then we would have written this, we would have put X's there, we would have put the magic numbers there, right? And you would have divided each magic number by A. Remember this? Okay, you divide each magic number by A. And then you're going to simplify the fractions if you can, right? So this one's going to become x minus 6, and this one you're stuck with x minus 3 over 2, and then finally you go bottoms up. So if you're stuck with a fraction, the denominator gets moved up to the front, and our final answer would be x minus 6 times 2x minus 3. Does that ring a bell?
Yeah.
Okay. Okay, good. So that works. I'm going to show you a better way to do that. That's tomorrow. And you can do it this way if you want to, but I think you'll like my way better.
Consistently or ugly?